Up next, we are going to be having a crash course in building reliable software. Now, the speaker is Ming Bei, and they are a senior software engineer. So at this point, I'll hand things over to them if they are ready. Let's see here. All right. Hey, there you go.
Hello.
How are you doing?
Good, good. How are you?
Oh, doing good. Thank you. All right. I'll hand everything over to you now. Have a great one.
Thanks. Let me share my window. 1 second. Okay, can you see that? I think you should be able to see the presentation. So
Yep, we can see the presentation. We can hear you loud and clear.
great. Okay, let's start. So today I'm going to talk about crash. So I think most of you have like experienced some sort of crash doing embedded development. So we all hate crash because that's kind of something that not fun to work with. So I've been building embedded software and shipping to a fairly large group of customers in the past several years. So today I'm going to share some of the experience of how to make a software more reliable. And it's not company-sponsored speech, so I can not share the actual numbers or any project details. So, but in general, you get idea of how things works. Yeah, let's continue with the first slide. So it's about like a gondola service technician. So if you have heard that there is a tragedy happened in Italy early this year, I think it's May, there's a cable car crash and killed many people. So yeah, the reason, after investigation, the reason shows that the accident was caused by a technician who intentionally disabled the car's emergency brake system. So that kind of sounds like ridiculous. That's something like never supposed to happen. So why? Generally, we believe that I won't be that guy for sure. That sounds crazy. Who is gonna disabling a emergent security system, right? So let's take a different case. Take a look at a different case in our like maybe day-to-day projects. So here is a project. So let's imagine a project. The internal test lasts for roughly half a year, and it involves hundreds of internal users, like using that application day by day, and it has countless unit tests, like thousands of unit tests or more, and integration tests run on the CI machine on each code change, and it also runs on each build every night or each shipping release, and also has a man test for each release lasts for roughly a week. So man test is like a group of people like using that application as a real user, and then that's for the purpose of long life and brute force tests. So talking about the code itself is actually pretty big. It's several millions of C++, and it's compiled with pretty strict flags, warnings as errors, like things like that. And sanitizers are enabled. And for each pull request, there needs to be 3 or more senior devs to approve that to get into the source code base. So that's pretty strict. Yeah, this is not a real project. It's just an example of how things works. So if you get looks pretty good. So if we ship that product to the user, what's gonna happen? So one of my project shipped to a small group of users initially, and we get 90% of the crash-free users per day. 90% crash-free per user per day. So not per user, 90% crash-free users per day. That means 10% users will have at least one crash one day. So if we have 15 million total users. That means like 1.5 million crashes per day. Well, that's not good, right? Let's go to the next slide. So what can we get from here? So so the test lasts for a maximum of hundreds of hours per day. That's the maximum we can do. That's we put a lot of resource on that. And on the other hand, the users will spend more than 10 million hours per day on the app because a large group of users keep using that. So what does that mean? It means an error is 100,000 times less likely to happen in our tests. Also means if a crash happens on the user side and the crash rate is fairly low, then that means it's almost impossible to repro that on our side. Yeah, no matter how much resources we put into the test, it's never going to be enough, considering that 100,000 times less. If we double the resource, triple the resource, or 10 times the resource we put into the test, that's far away from enough, right? So yeah, what we can do here. Let's come back and take a look at that tragedy again. So a service technician who disabled the emergency brake, what was he thinking about when he did that? What was the real problem? Here is a comment from YouTube. I think is really good. So basically, it's saying that if you claim that I've never seen it in 30 years of working here, that's what the gondola service technician said in the court. He mentioned that I've never seen it in 30 years. Almost in my life, it's not. It never happens. So it never happens in the entire life means what? So if we do a math, if there's like there are 10,000 cable cars in the world, and every single cable car runs for like 100,000 hours, and what does a person's entire life mean to of a crash happening for a single gondola like that? So it's basically it's not even scratch the surface. So so that's a common mistake. So making a judgment when you don't have enough data to support it. So he is making a judgment that it's pretty safe to disable the emergency brake because it's never happened in his entire life. But does he really have the data to support that? Entire life is far away from enough. Just like we saw, it's our test is like 100,000 times less than the actual user scenario. So if we ask ourselves a question, so is your software reliable? I asked that question to a lot of people, so I got answers like, I've been using it for a month and haven't seen a single crash. Well, my team members have been testing it for several weeks. I heard some companies said, hey, your software is pretty good and it's running on some critical missions. And yes, things like that. Some customer says, or haven't seen a complaint on the forum, things, blah, blah, blah. What's the problem? Is that you can kind of feel like that's basically the same as what the gondola technician mentioned. So I've never seen it in 30 years of my life, so it's kind of pretty stable, right? It's actually not. So here, let's first define that crash-free. So the term crash used here is to refer to something that unrecoverable. So it's an unrecoverable failure, like in our daily embedded software development, it means a segmentation fault, or illegal instruction, or out of memory killed by the operating system, or things that we cannot recover by ourselves, by the application itself. Yeah, so let's do the math again. Consider we have achieved a good 99% daily crash-free rate if we spend efforts to improve that from 90 to 99. And what that means, if we apply 99% crash-free for 15 million total users, which means it will still crash on 150,000 users at least once per day. Or if the crash is evenly distributed, it's usually not, but let's assume it's evenly distributed in all users, then in 100 days, each user will run into a crash at least once. So that means for an average user, the application's life won't last longer than 4 months. So it's what's the reliability of 99%? Is about 4 months. So is that real problem here? It depends, I think. If the application is like a casual game or non-critical like user application, some like a WeChat app, not saying WeChat is non-stable, but things like that, you get idea. It's fine to crash, and the user will launch it again, and it does very minimal harm. But what if it's a like a breathing machine, a critical device? You are trying to build a core component inside a breathing machine, a core component inside maybe a gondola or cable car. So what if that fails? That becomes a real problem. So you don't want a breathing machine to last only 4 months or will randomly crash in 100 days, right? So yeah, here's the chapter 2. So let's try not be that guy, and let's see what we can do here. So how can we be more confident about the software quality? So we anyway, we are going to release the software. We are not going to test it forever. Is there any ways we can do before that release? And in the end, after we press that button, we don't get fired. Okay. So here's the first idea, and I think is the most important one: to shift problem detection to the left. So that's a interesting idea. So what does that mean? Shifting the problem detection to the left. Let's take a look at this graph. So here is the graph of a development stage and defect. X-axis is the development stage from the concept, design, development, testing, commit, integration, and production. So as we can see, the defect cost goes up exponentially along the axis. So when we, for example, when we have an issue in concept or design, then it's fairly easy to fix. We can just, maybe the design is just a drawing, and we can fix that like in 1 second. When it happens in development and testing, like testing is unit tests. So when we found mistakes in development, we can maybe make a new pull request and take half day to get approved and get into another unit test and see if that's still repro. So fixing a development error is still fairly easy, but when it comes to the integration and production, things become very, very bad, because if you find an error in the production, then that means you have to either update all the products over the air, or somehow recall your product, or if you don't have any way to fix that, then users might return or even sue sue you, and or maybe lead to some bankrupt or very bad results. So the defect cost goes up from to the right, and is small on the left side. So the idea here is to move the problem detection from the right to the left. So what we can do here, I will introduce some of the ways to improve how we can do that by going from the left to the right. So here we start with the design phase. So when we talk about design, usually we will focus on how the software functioning. Like if we are designing a messaging app, we will about how it interacts with the server, how it shows the message to the user, what's the UI going to be, things like that, right? So it's pretty rare that during the design, people are spending efforts on making the design less error prone. So the first thing here is making a foolproof design. What does that mean? Foolproof. So that to explain that, I can use an example of if we used to have a project that we are evaluating which language to use. So we have choice of like C++, C, JavaScript, or Python, or Rust. So it depends on the problems. So if we are doing a chat application, so it doesn't make much sense to use the C++ because it costs much more to hire people like who can do good C++ code, to be honest. So it's much easier to hire someone less familiar with JavaScript or Java. So a design that based on C++ will be cost much more and error prone than the Java solution when you have there is a term when you have a certain amount of like plan to spend, like money to spend. So if you hire more Java developers who can produce equally good amount of code as the a small amount of C++ developers that can produce like high quality C++ code, the costs of two groups are very different. So yeah, making a foolproof design, and it will reduce the risk of making mistakes. Like if you design the project using Java, then it's less likely to set segmentation fault or have like C++ like foot shooting arrows. If you make errors in C++, people said that you have blown away your one of your yeah, let's go to the next chapter. Yeah, somehow it's not responding, but let's see. Yeah, during the development, there are many ways to improve. So I will pick an example of assert. Assert is a very good example of how we can control the quality of doing development. So because we use that every day, we all know what that is. So what's the problem with assert? So assert is good, but not that good. It has downsides. So first question, when does the assert failure happen? So usually it's in unit tests or integration tests, right? So when assert triggers, it usually means it's in a particular triggering scenario. So for instance, if you send your product to a small group of users, some of them reported that, hey, when I do this and your device just rebooted or failed, that's a scenario when user mentioned when I do this. So you collect that data and come back and ask your engineers to fix it. And that's a like error fixing loop. So if you do that, if you do assert, if you want to trigger assert in the unit test, then you might require a full code coverage. What does that mean? The full code coverage means the unit test can trigger any potential assert that's supposed to trigger. So if an assert is not covered by a unit test, that basically means who knows if we're triggering the wrong time, right? When you send to the user, if the user doesn't hit that scenario, then the assert is still like a piece of dead code. One is like ticking bomb waiting to happen someday. And the worst thing for assert is that it's disabled in production in most cases. People has like define assert to nothing. If define release, define assert to nothing. If define debug, define assert to something. So which means the only way to trigger assert is during the unit test, or you build a debug version and do that test or send to a group of users doing that. It's not going to happen on large-scale production. So yeah, that's the bad thing about assert. So let's take a look at another example using the assert. So here is the very simple function called +1. It does only one thing, to add 1 to a pointer, int pointer. Yeah, so we pass a pointer into the function and then dereference the pointer and +1 and return that value. So this function is very unsafe. Why? It's because, first of all, p can't be null, because that's a pointer. Of course, it can't be null. We need to assert p, right? And star p must be smaller than a certain value, because in C or C++, if the p is too big, in this case, if it's int max, star p, if it's int max, it will overflow. The overflow in C++ is undefined behavior, so we need to check that with another assert. And none of these limitations can be easily told without looking at the implementation. So you either let the user read this +1 implementation, or write all of them in the comments, and hoping the user will follow the rules, right? Which normally doesn't happen. Yeah, it's also unsafe at runtime. Why this is unsafe? Because when the assert goes away, this function becomes one line only, return star p +1. There is no safeguard. There is nothing to protect it from exploding if things go wrong. If any bad value passes into the p, then who knows what's going to happen. So what we can do from here. This is written in C++. It's just the idea of how we can fix that. It's not limited to C++, but C++ is easier to express ideas. You can do that with C or Rust or Java or anything. You can. Here we are returning. Optional means there's a return value. It's either a value or nothing. So so usually when you get an optional as a return value, that naturally means if the return value contains a value, then that's a valid legal return. And if it contains nothing, and then that's an error. It's pretty like self-explanatory. And here we're still passing in a p pointer, int star p. But in the first line, we check p if p is int max, because we are going to +1 on it. So it's checking the limit. Otherwise, return star p +1. So in this function, we have no limit on p. You can pass it like int max or out of the range p. That's fine, because we are going to check it in the code and return an optional none. And the function itself is pretty safe. And by returning the optional, you are clearly telling the user that you are going to potentially return a error. You have to deal with the optional. It's not like you return an int in the previous function. Like I get int from a function. So people usually think that int is the return result. Not necessarily still believe that what I have to take care of here, if someone is lazy, then just ignore that. But returning an optional is forcing the user to take care of that. Also, it's runtime safe. It's not like assert. If we compile as release and assert goes away, the function still runs and still safe, regardless of the input. Right? So, and also the function syntax is pretty much self-explanatory, and you don't even need to document. So if we want to write a document for this function, what we need to write? Like you have to take care of the return value. No, that's kind of, we already know that that's return optional. So it's clear that there's gonna return an error, right? So, or do we need to write, hey, you cannot pass a p that exceeds the int max? Not necessarily either, because the function will check the error internally and return error. That's how the function works, right? So basically, yeah, you don't need document. Also here we use the C++20 unlikely. That means that if branch is not likely to hit, so that improves performance quite a bit. So the CPU's like instruction pipeline will go with the go by default on the next, so you will relatively faster. So it's one of the example of shifting problem detection to the left. So what that means is to detect an assert error, we have to go to the integration test or send device to the user or have someone to trigger that. That's very late on the right side of that bar. So when that happens, the delay or the cost of the feedback and fix that issue is pretty high. So here, if we apply this practice on the code and detect an error during the development or during the unit test, then to fix that cost, the feedback loop is much smaller. Yeah, here's the next topic is about code review. It's still in part of the development process. So when we talk about code review, people usually believe that someone hate that, someone like it, someone said, hey, you are being picky, or saying, hey, just approve it, I need to get this done before tomorrow. Or it's like, what you said are all true, but I'm gonna fix that in the next pull request. I'm not gonna fix it today, or things like they have all different kinds of excuses. So I guess if you do code review, you must have seen that a lot. That happens even in a large company. It's human natural. So so when we do code review, what we need to focus on. There are tips too. So the first point is the code review should focus on what a computer can. So what a computer can do is that things like checking the syntax or try to do compile and static analysis in CI or running unit tests. All these stuff, let the computer do it. So if you are checking code styles or trying to point out some syntax errors, compile errors in the code review, then you're probably doing it wrong. You are wasting some of the developers' time. So let someone to write an automation script and run that on CI. Once the CI pass all the code checks, then after that, asking the reviewers to come and take a look. The second point is human is unreliable. So that happens a lot. So when we ask code reviewer to review the code, it's pretty likely a mistake get through and not detected by either of the reviewers. That's why we sometimes require critical change needs 3 or more senior devs to take a look. That's sometimes still not enough because human is unreliable. If you can run unit tests, so if you can control and shift some stuff into the computer, like you run unit tests into the computer, you can avoid like reviewers ask for things like, have you run it on your machine and verify everything works? This kind of question. So also, if you ask yourself, I'm letting A, B, and C 3 guy to review my code, do they really know my code? Do they really know? I think that might not always true, right? So if people don't understand your code, then that makes much less sense to review because, yeah, it's how it is. If you don't understand, how are you gonna review it? So if that happens and that guy is blindly giving approval, that's also bad. So what we focus on here for the code review, so design and implementation problems. So one of the examples is that you can see the line below. If we say, hey, based on the design, the object should be thread safe. So therefore, you are missing a mutex. So that's a very good review feedback. So that's from the design point of view, it's avoiding a disaster, and also that's something that a computer cannot detect. So that's something a reviewer should really focus on, I think. So yeah, next is the unit tests. I've seen many projects doesn't spend time or even have 0 unit tests in the project. So I'm going to say, in my experience, I've seen that a lot, and every time I have to emphasize how unit testing is important to the project, and in many cases, I just get ignored because like people don't like it, just don't want spending time writing something that's boring. You know, nobody wants to write unit tests, but trust me. So here, why is that? So unit tests here, I said, is the least expensive way to detect the most amount of issues. So it's least expensive, but it can detect most amount of issues. So the unit test has a guaranteed coverage. So if you write unit tests for your piece of code, you are trying to imagine what's going to happen for that piece of code, right? What's going to go wrong? So you put that idea into the unit test to test those right and wrong scenarios. And eventually you get a full coverage of that. Means all your code paths has been tested. It's either like correct production code paths for users, or either error handling logics for like rarely happen scenarios. All of them are covered. So we don't want to wait until really the user runs into that, like really touch the code and trigger that some kind of errors very later on. So it's also very easy to repro. So if you have unit test a failure, then yeah, you just hook up a debugger into the unit test, and then yeah, the debugger will tell you where is the failure. It's constantly repro and every day running on the CI machine, and once a commit breaks something, you know immediately. It's also a safeguard. So the safeguard is something especially, I think, critical for open source projects like RT-Thread. So for open source projects, like people contributing to these projects on functions, not necessarily unit tests. Like for instance, when we get contributions to like new BSP bring up or a new functional component, is always like, hey, I managed to run something on RT-Thread, right? That's exciting. I'm not saying that's bad, but have you ever heard like someone in the group saying, hey, I made a contribution to the RT-Thread and I added 100 unit tests? Well, that's yeah. So so if that happens, then we are constantly getting contributions to the community, and if we don't have anything to protect the foundation, to the ground, then the quality goes down very quickly because nothing to protect errors from happening. And people making contributions, they might break things. This broken stuff silently creep into the code without anybody detect that. Until one day, some other users trying to pull the code and run it on their machine, saying, hey, someone broke this part, and who did that? I'm gonna find him and like blame him or do something. Is that really his fault? Not necessarily, I think. I think it's mostly fault of the project, because the project doesn't have a way to protect the software quality to maintain the software quality on a certain level. Yeah, also the unit test is in fact examples. Personally, if I want to learn a new API, a new set of API, I would prefer to go to the unit test rather than to the documents, because unit test is something that shows you how the code should lay it down. It has it basically means what the code, what API are supposed to be used, and what API are supposed to return. So in each unit test, you are writing like, hey, I'm calling this API, and by passing in these arguments, then the API should return that. If not, then fail, right? Unit test is all like that. So by looking at the unit test, we know each input and output limitation requirements of each API, and we clearly from code clearly know the behavior of the function, rather than reading the sometimes it's not very good documents and try to imagine and write some code and try to do some tests by ourselves, and later on find some like exceptions or things like that. So there are practices to combine the unit tests and documents, like Rust doc test, which is a great example of combining unit tests and documents. So when you're reading documents, you say, hey, instead of stating how this function works, I will show you a couple examples. By looking at the examples, you know how you can almost like copy those examples into your code, and that's how things are supposed to work. So after all, never give up anything that's on the left side. And unit test is something that on the left side and can also help detect most of the amount of issues. Yeah, next point is about quick and dirty hacks. So that's also fairly happens fairly often. So in my past projects, I see that happens like almost all the time. People rush into some new features, or people rush into a bug fix, and he wants to get a ugly and quick fix into the code in order to fix a product, or in order to finish a feature. So when this quick and dirty hacks comes in, they always have a next excuse. If you have seen this, like someone come to you saying, hey, there is a bug. I need you to fix that before tomorrow. Then he come up with a bug fix, maybe just a error check or something, saying, hey, I don't know how that really happens. It might take a long time to investigate, but I need to get this done tomorrow. So here is a quick and dirty hack that if we apply this hack, then everything is good. So yeah, let's get this hack improved, get this hack in and approve this. So that's personally, I don't like that. But sometimes you have to make some compromises. But after that happens, if the code really gets in and fix the issue, that's not a fix. That's a hack. So quick and dirty hack, if we don't take care of that hack and let it in and forget about it, then it will almost always bite back. So what does that mean? So if in the previous example, that guy doesn't have a proper fix. He spent some time, but he's not able to pinpoint really the root cause of that issue. So so the root cause is still like lying hidden somewhere in the code, waiting to explode someday again. So when people applying that kind of quick and dirty hacks, they usually have some rules, like if we don't do this, then it's not going to happen. If we don't pass the object to something else, then that's guaranteed a safe or something like that. And these rules are not documented in many cases, and people will forget that. Once people forget that, it becomes a ticking bomb. And people will leave also. They leave with their knowledges. Someone fixed that issue half a year ago, and if you will try to find him, oh, he has left the company. Now nobody knows what he did means. He changed some code. Why? There's no document. If we touch that code, things break. Yeah, we stuck. So for quick and dirty hacks, I say, don't push the problems to the right. So quick and dirty hacks are essentially pushing the problems to the right. It's waiting something to happen on production or later in the pipeline. How do we know it's a quick and dirty hack? So usually when we feel that a code is ugly, well, you probably have to be more cautious. Like if that ugly code gets into the sources, then you might want to add a calendar item later to fix that in a non-ugly way, to rewrite it or do some refactor to clean that up. It's like a tech debt. You have to pay the debt someday. You don't want to pay debt later when the debt becomes too high, right? Yeah, that's about quick and dirty hacks. So here we come to the integration test. Integration test, if you remember the graph in the beginning, is fairly on the right side, because when we come to the integration test, it usually means the features are completed and people are trying to use that. You are shipping product. You may be shipping the product to a group of internal users, or trying to do some like feature testing, things like that. And it's when it comes to the integration tests, you will almost be a trade-off between test coverage and the shipping days. So let's imagine you have a month before the release date. Like your boss tell you, hey, you have to ship it before next month, and you have 4 weeks. What are you gonna do when the integration test lasts for at least a week? That means you have 4 tries. If you failed on 4 tries, then you are going to get fired, right? Integration tests is something we don't want to like shorten its duration, because the more we test the product, like the more confident we can know how the actual user use this production. So it's the only way we know how it works in reality. And it's also not enough for if we come back to the first example of the user scenario versus test scenario, is 100,000 times less than the actual user scenario. So even if we put huge efforts to integration tests, that's far from enough. So how much effort we put into that test is always a trade-off. So when we come to the trade-off, then it becomes like we are either postpone the shipping date, or to cut some features, or letting some bugs into the production. There isn't much choice in that situation, right? So it always comes at costs, and the cost is pretty high. So here's the quality checklist. So the checklist is I'm not saying you have to like strictly follow every bullet point and do everything. It's more of an emphasis or reminder of like some of the important things. Like if you have an error-proofing design, if you have a careful implementation, or code review, if your code review is properly executed or just ignored. Do you have unit tests to cover it? Unit tests with high coverage. Unit tests itself is good, but high coverage is better. Like when we have a coverage, then we know what part is not covered. Then we can have more unit tests and they give us a feedback of how unit test works, to prevent us overconfidence. So static analysis, CI system for doing those jobs, and integration tests. And so the second part is about A/B testing and percentage rollout. The A/B testing and percentage rollout is about things after shipping to maybe a group of users. That's after the integration test. That's maybe the final stage before you officially shipping your production product to all of your users. So we want to do A/B testing because we need to see how this works before an error gets distributed to too many users. First of all, let's face the truth. The truth is that A/B testing in the percentage rollout is a luxury, and it's not necessarily always an option. So, especially for embedded development, usually when we create a new board, write operating system and bring RT thread on it, and write application, and finally bring the products to the user, we don't necessarily have a way to get user feedbacks or even collect data from the real user scenarios. So here are some pretty good tools which can be used to do what we mentioned before, to collect data. So to collect data is you have to be careful. Don't collect some of the sensitive data from the user or violate the agreement between you and your users, you and your customers. So it's always you have to be careful and check the laws. But there are some tools like Firebase, Crashlytics, and Backtrace IO, and they can all do a cloud-based data collection. And when your device fails or when your application dies, then it somehow put the crash logs or stack traces and some of the selected non-sensitive user data to the cloud. And then later on, you can investigate the real users' data. And by only by doing that, you can know what's real look like. Because without those tools, basically we can only just imagine how things works, waiting for the user feedback or waiting for people's complaints on the forum, and yeah, that's all we can do. So by doing this, we can be innovative. So here, I think there are many ways to do that. Be innovative because different projects has different approaches of doing this, and it's very sometimes it's very project dependent. So for a native project, for a kernel, for application, or for Android or iOS apps, they all have different ways to collect the feedbacks. But the idea is that we need to have those feedbacks, so we can maybe even if we just send the questionnaire to the customers, that also is kind of a feedback, right? So what tools we can use to collect those data? What service team can we build a service team to connect the customers and get their feedback? Or can we build a automation tool that runs on some scenarios, and when the product fails, it feedback the data automatically? Or maybe even better, can we get call stacks or core dumps from the device, and so we can analyze it locally, repro that locally? So yeah, there's many ways for that, but the most important thing is try to do that. Have that in mind is more important than like how to actually doing that. If you think about that, it's just about like a couple of different ways, but that's something usually get forgotten. Yeah, other than that, I'm going to talk about the big and small changes. So here's a pretty interesting story. So when we talk about big and small changes, we usually know that making big changes before release is bad. Like people think, hey, you can commit 1,000 lines because tomorrow is a shipping day. You are downgrading the quality. Who knows what's going to happen in that 1,000 lines? Or I can say, hey, I just added one line and that looks like pretty safe. Is that true? Not quite. I can say, in my experience, I'm not saying it's always like that, but in my experience, I've seen the opposite. There's a real case. Again, this speech is not company sponsored, so I can not say any numbers and or any project details, but you get the idea. So there is a small change. So after a small change, one of our product has a 20% crash date. That's a huge incident. So 20% is that's a lot. If we have like 15 million users, then that means like how many users are going to crash? 30 million users. So what I need to emphasize here is the big or small changes are sometimes illusions. I mean, illusions means that's not always holding true. So when we make safe changes, what happened for the previous project, what we made here is a change that only adds a couple of null checks. So it's pretty safe because it's just adding null check. What can happen with null checks? So for a project with a multi-million lines of code, a tiny change might have a butterfly effect. So what happened here is that the tiny change, the safe change, caused a memory layout shift, which eventually revealed a previously undiscovered bug in a different place. So before this commit, then something bad was happening, but a pointer was maybe pointing to some garbage memory, and that memory was actual garbage, so that's fine. And after that, the garbage is no longer garbage. After the memory shift, it points to some critical area. And that's scary. So the more scary part is that if we don't have the crash data collected from the devices, we wouldn't even realize that until maybe someone complains or like we get customers' feedbacks in a bad way, in a like really huge complaint, considering about 20% did. So how can you fix that? There's one easy way is to component isolation testing. So what component isolation means? Here on the right side, there is a graph about, I just borrowed a random graph from the website or from the internet. It shows layers, and on each layer we have different components. I think many projects are designed this way. Don't need me to emphasize more of that. But the idea here is once you have component, don't treat the component like a cleanness of the code. The goal of having component is not the component itself. It's not separating the code. The goal is to have a API layer boundary and fully test that API layer boundary. So it's like you have a bunch of components. Then components interact them with each other with a contract. That contract is the API. You test those APIs. So that means a component behind that API, the behavior stays the same. So if you make change to one component and then leaving the other unchanged, then you can safely assuming that something living in that component is safe. Or if you have changed to both component and then you don't change the API, And the unit test on those API layer also doesn't need any changes. That means you are keeping a stable layer between components, and also means you are isolating the impact of a change inside those components. So what I want to emphasize here is first to have a clean layer API boundary. The API boundary could be a list of functions or some objects, but you better not having something like external static variables or that kind of thing in the API. And fully test those APIs. Fully test means each API, if it succeeds, fails, every scenario needs to be tested. All the combinations of different APIs, all the usage of the APIs needs to be tested. Who is responsible for the tests? So let's say my example was when we use a component like a curl or FFmpeg in one of my projects. So when I call curl, when I use a component, I need to use that in my way, a subset of features, a subset of functions. So I call those functions A, B, and C in a particular order. So what I need is that I'll make sure when I do this, when I call the functions this way, it has to work as I expected. So I create unit tests for this particular scenario for that component. In that case, no matter what the component changes, as long as my unit test passes, I can guarantee that my use scenario on this component is valid, is still good. So nothing breaks. Component itself might also have some unit tests, but that doesn't necessarily cover everything, cover every scenario I needed. So I hope in practice, like when different groups interacting each other, the users needs to focus on some of the unit tests for the components that he needs to use, like to guarantee the safety of the contract, which is the part of that API. Let's continue about this. Let me take a look at the time. Okay, I'll be quick. So what does that crash? How about some crash-free techniques? So I have some ideas about crash-free techniques. So we don't like crash. Can we use some way to work around it, like user space versus kernel space? When user space application dies, the kernel can launch it again or somehow restart the application. In traditional RTOS, when application dies, sometimes it just carry the kernel into some bad state, and it's almost not pretty difficult to recover. And by separating the user space and the kernel space, you are building a safety layer between the application and kernel, and your application, your entire project becomes safer because there is a way to reboot the application. Like if you are using RT-thread Smart, that's more safer than just using a traditional RT-thread RTOS kernel. Or you can also use a VM-based runtime like JavaScript or Lua, Python, or WASM. So when we say a controlled environment, that means the application runs inside a container. Like that container usually don't crash. So if we have a JavaScript container, you have exceptions, it throws exceptions, and then when we get exceptions, then we restart the application. So you get the idea. So, but the environment itself might crash when the JVM crash or kernel crash or like JavaScript runtime crash. It still happens. But the having a separate between the environment and the application running inside that, we are actually separating our application into two parts, and the goal of two parts are different. I think that is key to keep both components reliable. For instance, if we use the traditional RTOS, we are mixing kernel and applications, and each one of them dies and brings the other to the a bad state. So by separating the kernel and the user, or separating the VM and the application running in that, we can essentially build applications, build all the feature requests into the application, and the environment itself. The goal of the environment itself is not to add features, but to stabilize it. So two parts, two different goals. One part is for stabilization. One part is for feature rich. So when customers has more feature requests, I say, hey, I can add this feature to the application, and not degrading that the kernel's stability. And also embedded OS and drivers. So drivers in this case, I think, is particular tricky case, because we get, just like we get user requests on features, or like customers request on changing some stuff. It happens a lot, and different board has different drivers, and different board has different configurations. Thus, we need something to handle those differences, and something that tends to be changed a lot. So that's kind of fall into the application group rather than the kernel, the environment group. So the goal of the environment is to stabilize. Something changed rapidly is not going to help the stabilization. We need to avoid that. So avoid kernel to get changed too often. So what can we do here, like using microkernel or using user space drivers to handle those frequently changed stuff? Yeah, you can be innovative, but the idea is to move those frequently changed stuff out of the component that you are supposed to stabilize in the long run. So there are more crash-free techniques, like can we make the environment crash-free? Like we use a kernel. The kernel itself is written in C, and it still might crash sometimes. Or maybe we can use Rust, or Rust rules out all the memory issues. Or we can use maybe for a VM-based environment, for WebAssembly, we can use compile C into WebAssembly to make it safer. Yeah, things like that. We can try to make the environment be more robust. There are ways to do that. So that's my conclusion. So if we go back to the Gondola technician claims, he said, I think Gondola is pretty safe because I haven't seen any of these in the past 30 years. That's a claim to justify his action of disabling that emergency brake, and that's not good. So we don't want to be that. So how can we make our software more reliable? Do we have a good design and careful implementation and a meaningful code review, and having unit tests and high coverage? Unit test covers most of our code, especially the error cases. Do we have the integration tests to simulate the real user scenarios? And eventually, we need A/B testing, the percentage rule out, and feedbacks to know what the real what's going to happen when we ship the product to a group of users. So when your product is in the reality, in the user's hand, what's going to happen? So we need to know that. So more of this is done, and then more of the claim is true. Like, my software is reliable. Is that really reliable? Yes, we can say that confidently. I hope everyone can say that confidently, rather than just a bold claim. So that's, I think that's everything. And thank you. Thank you for listening to me for such a long time.
All right. Thank you very much for a great presentation. Very thorough. And honestly, one of my favorite topics. So it's absolutely fantastic. Thank you for putting that together. That was really great. So I guess what we can do here real quick, I think maybe I'll check let me check the chat and see if we have a question or two that we could have you answer, if you don't mind. And then we can, then we'll keep the conference rolling here. I thought I saw a couple of good ones in here a little while back. Let me see here. Yes. Do you recommend following some standards such as MISRA or CERT?
Foreign standards is great, but my experience that standard sometimes doesn't fit very well into your product. Sometimes when we go to a standard and say part of it is, and it doesn't 100% like cover all my scenarios. So in my personal experience is that you have to always be innovative to invent your own like ways to do these things. I think when you think about standards, then you already start to think about things like how to make software reliable. And then once thinking about that, I think that's the most important. That's already pretty good. So the problem with most projects is that they don't care much. That's the biggest problem.
All right, excellent. Perfect. We greatly appreciate that. And I think you might have mentioned it in the talk, but I see someone was asking a question. Which framework are you using for unit testing?
For C, I'm using C. It's called Unit C or something. Yeah, for most tests are in C++. It's Google's GTest suite.
Okay. So you're mostly using the Google one. All right, fantastic. We greatly appreciate that. So there may be an opportunity too to continue to interact with the attendees by going over into the comments, and there might be some additional questions you see in there. So feel free to please take a look there as well. And thank you very much again for the presentation. And we will let you have a good rest of your day while we continue the conference. So
thank you.
Yep. Thank you. So everyone.